Okay. Okay. So good morning. Welcome everybody to the third day of our conference. So it's my pleasure to present Arzu Ahmadova from the Eastern Mediterranean University, who is going to speak about discrete time, mean field stochastic optimal control problems. Please, Arzu.
Okay. Thank you very much for giving the opportunity to give a talk in this presentation. My main research interest is related to optimal control theory, and I will start having some topic discrete time mean field stochastic optimal control problems. And let's start first the motivation. Why study this problem? What's the main gaps that which has been not studied yet? And let's start first giving that the main motivation that I'm going to fill in some gaps, stochastic optimal control theory, and especially discrete time stochastic control theory. And then we use this finite approximation method since this is discrete time. Stochastic optimal control, we use this time and discretize the time. And then this method also can be applied in the more complicated problems, such as the problem with delays and problem with terminal constraints, and also some neutral term. And also this has a big application to fractional dynamics that one can consider the fractional optimal maximum principle. Yeah, there are still papers which has been done, some other authors, but in the numerical sense, not in the pure sense of this optimal control theory to fractional dynamics. The next, this is constructive method, is that when the necessary condition is also sufficient, and also we prove here that we needed some other certain hypothesis to apply the necessary condition, which is that also the sufficient condition. And finally, the most important part, every theory has a application beyond. So, and this is the application done already for the linear quadratic mean field control theorem. And we adapt this practical application based on the main theorem, which we can tag there. And we can see the discrete time system in summaries in the investment process. But the time duration, I will not consider that part, but it will be already accepted by the journal. So you will maybe soon see online. Next, in order to start the statement of the main idea, I will give some notations that will be used in some standard calculations and in the proof of the theorems and the lemmas, and in order to get the elegant form of this solution. So this is the sequences omega tk, sorry. This is the sequence omega tk, that omega tk is a sequence of f measurable RD valued random variables, and this is the difference omega htk that with k starting from 1 till n. That's why this condition, and this condition will be very helpful to conduct some standard calculations, which is this expected value of this omega htk. The expected value of this with respect to fk measurable is equal to 0, and the rest is some other noun condition. Here is delta ml, 1m equal to l, Kronecker delta equal to 1, differ is equal to 0. This is the identity with appropriate dimension identity matrix. The next, this is the statement of the main result, that we consider discrete time stochastic nonlinear optimal control problems of mean field time type, and which is called Y mean field time because we have here the expected value of this xt optimal state problem. And now we have here expected value of xt, and here also. And if we take this, the expected value of
the link, I don't know, the link should be in the bulletin. I don't know if I can't, but I can't see it there either. People are here.
Now we can also almost there.
Yeah. Okay. So that when we find the expected value xt t plus h, and we will have the expected value of this and expected value of this part, but this part will be 0 because of the Brownian motion. Expected value of the Brownian motion is equal to 0. So then here is this t is the tk t0 plus kh, which is for all positive h, and that's the things is the finite approximation method for the discrete time stochastic optimal control problem, we take in each part, and this is will be good seeing that in the proof of the lemmas and the theorems that we take each part. For example, for we start T0, then T1, T2, and etc. So yeah, we introduce the cost functional, which we need to find some optimal solution pair that minimize the cost functional this. And then we have some function here, phi and L, and this is the introduction of this. And we will use some shorthand notation for LF sigma j as a psi in order to simplify our solutions. And this is the sequence of F measurable other random value variables, which I taught before. Now I will introduce this admissible control set. So here's UA, the admissible control set consisting of U, which is equal to UTK. And here is R to the power R dimensional. Then we have an UT, which is a complex subset of this R to the power R. And then we need to solve this problem for S, which we need to find the optimal value V that minimize the cost function over UT. And here, this is called optimal control. So this is the X is optimal state process, and the pair is optimal pair. So we need some assumptions in order to state the theorem. And here is, yeah, we apply the Lipschitz condition, and then derivative, we assume that this psi be continuously differentiable with respect to X. Then we use this. And then the H3, this is UT is closed, and the set F sigma 1, sigma 2 is convex. Yeah. Now, yeah, we are going to state the main theorem, which we need to solve backward stochastic difference equation. We get two pair, P and Q, and let's do this. Under the assumption A1, A2, we assume that the function phi satisfies the Lipschitz condition in the neighborhood of the point xt, xt and plus 1 and differentiable at that point. So there is a solution pair that PQ1, QD, and this is the solution of this discrete time backward stochastic equation. So of course, this coming from the end to the beginning. After proving all the steps, and we will need some lemmas to prove this theorem. For this, we fix a time t0 and choose the v in L2 omega f measurable set, and such that u theta plus this delta v in u theta, and we define the perturbed admissible control. This, and yeah. So convexity of U theta implies that the control U epsilon is admissible, and let X epsilon be a solution of the main problem corresponding to the control U epsilon. Yeah, this again, the following shorthand notation will be helpful for this lemma 2 and lemma 3. Those are the main swing lemmas that we need to prove the first these, and then going to the proof of the theorems. And yeah, this lemma 2 is correct. It is through under the assumption A1, and then this is the difference, expected value of the difference x epsilon and x hat, which is less than or equal to L epsilon square expected value of the gradient. I'm sorry, delta v square. So then we have this. Once we have this, and then we're going to have a first order increment of the cost functional, and in order to prove this, here we use it u epsilon spike or needle variation of u hat. We define this, and in order to find the difference of this cost functional, we apply the first order Taylor approximation, and this is the proof, the sketch of the proof based on the following identity for discrete time stochastic optimal control problem. Just we need to first find the right hand side first term of the right-hand side, then second term of the right-hand side, then we will find the last answer. This is this. So yeah, in the beginning, I already gave this PT and +1 in the main problem. We will use the expression of these in order to get that part. And here there are some calculation that, which is, of course, skip it here. And with the help of the lemma 4, which is the cost, the increment of the cost function, this follows from the fact that which is 4 we get, and then where this the Hamiltonian function is differential with respect to u, which is this. And finally, we deduce the variational inequality from 4, and therefore we prove the backward stochastic differential equation theorem. And then some sufficient conditions for optimality. In order to prove this, we need some assumption h1, h2, h3 that phi is convex in x, y, and functions f sigma l are convex, and Hamiltonian h is also convex, and the function f sigma phi l with respect to the derivative of this with respect to y are non-negative. This seems here that in this part we get it that's minus epsilon this, so that's why we need to consider that those are non-negative. So we state the theorem 5 under the condition h1, h2, h3, and let u hat in the admissible set. From the admissible set, we state the trajectory x hat be given and such that there exists the pair pqj to the adjoint equation. Then if Hamiltonian function x hat u hat pq, which is the infinitum of this Hamiltonian function, and where v is in ut, the complex set. And then we say that, okay, u hat is also optimal control. Now we denote some notation here. Since phi convex, we can use this. Following inequality holds true. And yeah, of course, this is after some calculation to reach this part. And here we use it in the main theorem. We already mentioned the PT and +1. So we use it later. This, the first term of the previous expression will be this, Ptn +1, x hat Tn +1 minus xtn +1. So after some calculation in the last step of this, and yeah, we come up here, we differentiate the Hamiltonian and use the convexity of the function to get this inequality. And where we applied here that in the last step that hu u hat u is less than or equal to 0 due to minimum condition, which was already mentioned before. And then, yeah, combining these all inequalities gives us that u hat is an optimal. So there are, yeah, this is the first, this shows that sufficient is necessary. First of the necessary condition is also sufficient condition. And yeah, we have some future directions that what about the second order necessary condition for discrete time infield type stochastic systems. This is also ongoing projects that I'm working on, application of optimal control theory for fractional dynamics. So the interesting part is to investigate the maximum principle for Volterra integral equation with singular kernels, and then deriving the backward stochastic difference equation for functional or delayed differential equations. And of course, for all problems, we will have the different backward stochastic difference equation will be different from the main theorem, which we conducted here. And the main difficulty for stochastic maximum principle is the stochastic the optimal control theory governed by even continuous time, not even discrete time. Difficulty is that the stochastic differential equation involves stochastic integral, which is the order of the epsilon, but we have a hidden complexity phase there. So that's why one can apply the first order, should apply also second order necessary condition to achieve the result. Yeah, there are some references that I use it in this theory. There are Gomyonov, Mordukhovich, and also my supervisor Nazim Mahmudov papers will be helpful to for the beginner to start for optimal control theory of stochastic differential equations. Yeah, this is already, yeah, accepted, and then thank you for your attention.
Any questions, please, to the speaker?
Yeah.
Enrico, just 1 second. No.
So I wanted to ask you, you touched it upon just at the beginning, but the main motivation for this work, if you have some time to explain what was the problem that motivated you to work on this particular problem.
Yeah, actually, optimal control theory, the stochastic maximum principle, has many applications in finance, economics, and in the beginning I said that has an application to the finance, which I created discrete-time system in risk investment process and optimize the user optimization problem to having some experiment there. And this is already done. And also another application to linear quadratic problem. That's again our backward stochastic. We have a difference Riccati equation, which is completely different and complicated to get, but different method we use it there, and to achieve this result.
Any other questions? Astrid, anything from your side?
Yeah.
Yes.
Yes, maybe just a remark. So in fact, you consider mean field dependence only through the expectation, right?
Yeah.
And your backward difference equation is in fact the analog of the backward stochastic differential equation derived by Carmona and Delarue in the continuous time case.
Mm-hmm.
So I'm wondering why you don't consider general dependence with respect to the law of the state, because in their work.
Without, you mean mean field?
Yes. So
yeah, it's already done. With mean field types, without mean field type, this.
No. I mean, because here you just consider mean field with respect to the expectation, but not respect to, in general, with respect to the law of the process.
Yeah. And there are some references that already mentioned those parts in their work. So in order to not use the repetition on that theory, which they use it, that's why especially can see that this mean field type stochastic discrete time optimal control.
No, but you consider very specific dependence with respect to the law, because.
So the logic is to get the backward difference equation,
yes,
and Riccati equation in the application of the linear quadratic problem.
Okay.
There is also application here, and we use this main theorem, apply there to linear quadratic problem, and to get the Riccati difference equation and prove it that, yeah, this is the solution. And this.
Okay, I understand for the linear quadratic case, but I suppose that it would be possible also to derive the general backward difference equation in the general mean field dependence, as in the work by Carmona and Delarue.
Yeah, it can be. Yeah.
Okay.
Thank you. Any other questions? Thank you very much.
Thank you.
Minutes.